Okay, so in this video, we're going to go over compound stoichiometry. Compound stoichiometry is a method that allows you to convert between equivalent units of measurement using a conversion factor. So let's talk about what a conversion factor is. A conversion factor is the same amount of something described in terms of two different units. So let's look at an example. Here is our example. 1 case of soda is equivalent to 12 cans of soda. Okay. So this is something that hopefully you've seen in your life. I'm assuming you probably have. So a case of soda contains 12 cans, and 12 cans of soda is what makes up 1 case. And even though I'm using different units, case versus cans, these mean the exact same thing. Okay. It's like saying 1 day is equal to 24 hours. Different units, but it's the same quantity of time. 1 case of soda, 12 cans of soda, different units, but it's the same quantity of soda. If I were to take the amount of soda found in a case and pour it into a giant graduated cylinder and do the same thing with 12 cans of soda, I would have the same volume because they're the same thing. They are equivalent. So I can use this relationship, this conversion factor, to allow me to convert between those units. And this particular setup, because it's something that you're familiar with, you could just do it automatically. If I asked you, how many cases would X number of cans be? Well, you would know how to do that because it's math you're familiar with. But as soon as I change my units from cases and cans to grams and moles, it seems like you guys start to think it's hard. It's not hard, it's just different. So as we're going through this compound stoichiometry piece, if you start to feel like you're getting in the weeds and you start to feel like you're a little bit confused, go back to this idea, because this conversion factor and this method of converting units, when I talk to you about it in terms of the cases and the cans, you get it. It's the same thing. We're just using different words. All right, so let's look at our first example. To complete a conversion, you have to set up an equation so that your units cancel out. So it allows you to not only convert the quantity you have into a different numerical arrangement, but the units as well. So let's look at our first example. If you have 736 cans of soda, how many cases do you have? Well, just kind of in life doing this, all right, if I have 736 cases or cans, and there's 12 cans in a case, divided by 12, that's going to be my cases. Well, that is exactly what you're doing. We're just setting it up on paper so that the units cancel and we can represent our value in the appropriate new units. So when we set up a conversion factor or a conversion problem, we always start with the number given in the problem, which in this case is 736 cans. Cans is my unit. I could even say cans soda include a substance, but for this example, I think that would be a little bit of overkill. I want to convert from cans to cases. In order to convert from cans to cases, my unit of cans has to go on the bottom and my unit of cases has to go on the top so that my cans will cancel out and it's going to leave me in cases. So this setup here represents my conversion factor, the same one we had up here. I can use this conversion factor in either direction and it still means the same thing. So I want to go from cans to cases. So 1 case of soda, which is going to be on top, is equivalent to 12 cans on the bottom. So 1 case over 12 cans. And so when I do the math, right, it's just 736 divided by 12, which is what you knew it was going to be all along. You're just doing it in a way that you can represent those units better. So 61.3 repeating. All right, so then let me think about our sig figs. This is a conversion factor. These are actual amounts. It's 1.000 infinite zeros, 12.000 infinite cans. These are counted values. So I'm going to ignore that for sig fig purposes. I'm going to look at what went in. What went in goes out. So this is 3 sig figs, 1, 2, 3. So this is 61.3 cases. of soda, which means I have 61 cases plus a few additional cans, right? It didn't come out to be a whole value. All right, let's go the other way just to prove the point. If I have 154 cases of soda, how many cans of soda is that? Well, 154 cases. We know that each case holds how many cans? Each case holds 12 cans. You would figure this out without having to do this method. So 12 cans on top, one case at the bottom. Cases and cases are going to cancel out. It's going to leave me in cans. 154 times 12 would be 1,848. If we're looking at this in terms of sig figs, 1, 2, 3, 1, 2, 3. This is going to round, so 1,850 cans. Okay, so we're going to do the exact same thing here in a second, except for instead of cases and cans, we're going to talk about grams and moles, but it's the exact same process. You're still just setting up a conversion so that your units cancel and you're left in the new unit, right? So whatever you're getting rid of is always going to go on the bottom. Whatever you're trying to go to is always going to go on the top, okay? All right, so next thing we're going to look at is the mole highway. So this was also in your notes. This is a good, helpful visual representation of how you're going to perform these types of conversions. So at the center here, we see the mole. The mole is the central unit. The mole is our dividing unit. And I can convert back and forth between moles to mass or particles or volume in one step, okay? On my highway. I got to stay on my road. If I stay on my road, I can make a conversion. So I can go from volume to moles and moles to volume. I can go from moles to particles and particles to moles. Particles representing atoms, molecules, or formula units. I can go from moles to mass and mass to moles. But can I go directly from mass to particles? Well, no, there's not an arrow there. There's not a road there. But can I go from mass to moles and moles to particles? Yes. So this idea of mole allows us to unite a bunch of different units. Same way I can't go from particles straight to volume, but I can go from particles to moles and moles to volume, or volume to moles and moles to mass. Okay, so this diagram is a good thing to keep in front of you when you are doing these conversions, especially if you're just learning, because it gives you, again, that visual representation of what's going on. Now, the stuff I've written here in pink, these are the actual conversion factors you're going to use to do these particular conversions. So let's talk through those real quick. As I'm going from moles to mass and mass to moles, my conversion factor is molar mass. If you don't remember molar mass, there's another video posted on molar mass. Remember that molar mass is the number of grams of a substance found in 1 mole of that substance. So when I calculate the molar mass, it's in grams per mole. Well, how many moles per 1 mole? So that's my conversion factor. X number of grams is equal to 1 mole. 1 mole is equal to X number of grams. When I go back and forth from moles to volume or volume to moles, I'm using a value generated by Avogadro. Not Avogadro's number, but the molar volume of a gas. 1 mole is equal to 22.4 liters. 22.4 liters is equal to 1 mole. That value is found on your reference packet in the big table on page 1. So one mole of any gas at STP, STP stands for standard temperature and pressure, is 22.4 liters. Okay. Going from moles to particles and particles to moles. 1 mole is equal to 6.02 times 10 to the 23rd. Now, I know on your reference packet it says 6.022. I will always use 6.02. I would prefer that you as well use 6.02. That's more often what you actually see used at higher levels of chemistry, even though it does go out longer technically in value. The 6.02 is sufficient. So Avogadro's number, 6.02 times 10 to the 23rd. That is the number of atoms to 1 mole. It's also the number of molecules to 1 mole. It's also the number of formula units to 1 mole. So really useful number. So there's 2 groups of problems, conversions, that we're going to look at in this video. 1-step problems and 2-step problems. So how do I know, do I have a 1-step problem or a 2-step problem? If you are given moles in the problem or asked for moles. That tells you it's a one-step problem. From moles to volume, one step. Volume to moles, one step. Moles to particle, one step. Particles to mole, one step. Moles to mass, mass to moles, one step. A two-step problem would be if I am going from mass to particles. Notice that moles aren't mentioned, but I've got to go through moles to get there. Mass to moles to particles. Particles, moles to mass. Volume, mass, or mass moles to volume. Volume, moles to mass. Particles, moles to volume. Volume, moles to particles. Okay. So we're going to do a series of one step first, and then we'll do some two-step problems. So here is our first problem. How many moles are in 25 grams of NaCl? So my starting point here is 25 grams of NaCl, and I'm being asked to go from grams to moles. How many moles are in this amount of grams? So I'm in grams, I'm in mass, I'm going to moles. That means that my conversion factor here is the molar mass. So the very first thing I need to do is calculate the molar mass. So I'm going to go ahead and calculate that off to the side here. So just like we did in our molar mass video, I've got Na, I have Cl, I have one Na, I have one Cl. I go to my periodic table and I find that the mass for Na is 22.99, that my mass for Cl is 35.45. I don't need to multiply because there's only one of each. I just need to add, and this comes out to be 58.44 grams per mole. Okay. So grams per mole. So that's my conversion factor. Now I'm going to set up my conversion so that my units will cancel. So starting with 25 grams of NaCl times. Remember, whatever I'm getting rid of goes on the bottom. So my grams of NaCl go on the bottom. And what I'm going to, which is moles, moles of NaCl go on top. And now I need to fill in my conversion factor. 58.44 grams is equal to 1 mole. So 1 mole is equal to 58.44 grams. All right, so my units cancel, and it's going to leave me in moles, which is the desired unit. So 25 divided by 58.44. I could go times 1 divided by 58.44, but that's overkill. You guys know that anything times 1 is itself. So that comes out to be 0.427789. All right, so let's talk sig figs. 25 has 2 sig figs. 58.44 has 4 sig figs. This is obviously less. This is exactly 1.000. So I'm going to go based off of the number that I have here. In general, most of the time you're going to see whatever's given in the problem is probably going to be what determines your sig figs. So 2. So 1, 2, the 7's going to round over. So in my answer, remember, my answer should always have 3 things. It should have a number, 0.43, a unit, moles, and a substance, NaCl. Failure to include the unit and substance is -1 each thing. Okay? Number, unit, substance. Got to have them all. All right, let's look at the next problem. How many grams are in 0.25 moles of KCl? So this time, I'm already in moles. It's asking me to go and find grams. So molar mass is still going to be my conversion factor. So my substance this time is KCl, which means I need the molar mass for KCl. So I have K, Cl, 1K, 1Cl. I know from my previous problem, my Cl is 35.45. Let's go find the K. 39.10. I don't need to multiply, I just need to add. This is 74.55 grams per mole. All right, so now we'll set up our conversion. So we're starting with, in the problem, 0.25 moles of KCl. And before I get too far into this, you will see mole abbreviated as MOL. Even though it's only MOLE, you will see it as MOL. Molecule is never abbreviated. It's always written out. Why they took a 5-letter word and made it a 3-letter abbreviation, but then left molecules, I will never understand. But do know that MOL is mole, not shorthand version of molecule. The more you know. All right. So I need to set this up so my units will cancel. I'm asked to find grams. I'm getting rid of moles. So the moles need to go on the bottom. So moles of KCl on the bottom, then grams of the KCl on the top. So 1 mole is equivalent to 74.55 grams. So I've set this up. My units cancel. It's going to leave me in grams. 0.25 times 74.55 gives me 18.6375. Okay. Sig figs, I've got 2, 4, so I'm going to have 2, 1, 2. The 3 is not going to round, so this is 18 grams of, oops, I wrote that down backwards. Darn my number dyslexia. This is a 6. This is a 3. This actually is going to round. 18.6375, not what I had written down. The 6 does round. This is 19 grams of KCl. All right. Pays to look at that calculator more carefully, huh? Okay, so that kind of takes care of the math side of our highway. So now we're going to go down our particle side. So moles to particles and particles to moles all uses the same conversion factor. That 1 mole is equivalent to 6.02 times 10 to the 23rd atoms, molecules, or formula units. It does not matter which one of these things you're going to. It's still atoms, molecules, or formula units is Avogadro's number. So I could pick any of these. Just for this problem, we're going to go with, we're doing atoms, right? But they're all the same. They're all particles, right? The only thing that's going to change about this is the unit. I could have atoms or molecules or formula units, but the number is still going to be the same. How many atoms are in 34.3 moles of Ca? So 34.3 moles of Ca times. I've got to get rid of my moles. So moles of Ca go on the bottom and atoms of Ca go on the top. 1 mole is equivalent to Avogadro's number, 6.02 times 10 to the 23rd. And that's it. I don't have to calculate anything ahead of time like I had to do up top where I had molar mass. This time I just use that constant. Now, anytime you are using Avogadro's number, it would be a very good idea to put it in parentheses, whether it's on the top or the bottom. It's going to especially matter on the bottom, but if you just get into the habit of doing it anytime you use Avogadro's number, it's going to kind of prevent you from misinterpreting, or for your calculator rather, misinterpreting what you mean. 6.02 times 10 to the 23rd, close parentheses. So I get 2.06486 e to the 25. Remember, e is the 10 to the x. Do not write e on your paper, 10 to the x. So let's write down 2.0648 times 10 to the 25th. And let's check out our sig figs. I've got 3 here. This is a constant, so I ignore it. So 3, 1, 2, 3. The 4 doesn't round. 2.06 times 10 to the 25th atoms of Ca. Okay. All right. Now let's look at our next one. Number 4. How many moles are in 8.42 0.28 times 10 to the 23rd F period U period formula units of Na. All right, so I'm still on that same side of the highway. My conversion factor is still Avogadro's number. So I'm going to just go ahead and set this up. I don't have to pre-calculate anything. 8.428 times 10 to the 23rd formula units Na times. It's asking me to find moles. So moles goes on the top. Moles of Na over formula units of Na. 1 mole is equal to 6.02 times 10 to the 23rd formula units. So let's go ahead and type this in. 8.428 times 10 to the 23rd divided by parentheses 6.02 times 10 to the 23rd. And that gives me 1.4. So let's talk for a second about why I said put it in parentheses. Watch what happens when I don't put it in parentheses. 6.428 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. Do you see how my number is very different? 1.4 times 10 to the 46th. What your calculator interprets when you don't put it in parentheses is I'm going to take this number, I'm going to divide it by the 6.02, and then I multiply it by 10 to the 23rd so that my powers don't end up canceling out. But obviously they should. Math logic tells you that they should. So when you're dividing, if you don't put it in parentheses, this is the problem you're going to run into. That's why I always say, if you've got Avogadro's number, just put it in parentheses. Save yourself the error of doing it wrong. All right, so 1.4. So let's look at our sig figs. 1, 2, 3, 4. Remember, this is a constant, so we don't do anything with this. But 4, I've got 4. I only have 2. How do I fix that? What do I need to do? What is our option if I don't have enough significant figures? Oh yeah, add zeros. So I'm going to add some zeros. So I'm going to add 2 zeros, and now I have 1, 2, 3, 4 sig figs. Now what do I need to add? Oh, I need units, moles. I need substance, Na. Box off my answer. Okay. All right. So our last part of the highway is the volume part. Let me flip back to the highway really quick. So for the volume part, moles to volume, volume to moles, our conversion factor is the molar volume of gas. 22.4 liters is equal to 1 mole. So again, for volume and particles, I don't have to pre-calculate anything. That makes it really quick. I only have to calculate if I'm in grams or if I'm asked for grams. If I'm in these two things, I just use these constants. So let's look at number 5. How many moles are in 3.20 liters of O2 gas? All right, so 3.20 liters O2 times. I need to get rid of liters, so liters are going to go to the bottom. So liters O2 on the bottom. What goes on top? Moles of O2. 1 mole is equal to 22.4 liters. That's going to get my liters to cancel out and leave me in moles. So in my calculator, 3.20 divided by 22.4 comes out to be 0.142857. That's overkill. This has 3 sig figs. This is a constant. It does not count. So I'm going to go on these 3 sig figs. 1, 2, 3. The 8's going to round. 0.143 moles of O2. Okay. All right. And for the last one, how many liters or what is the volume? I'm just giving you 2 different ways that you could see this question. How many liters of, or what is the volume of 1.75 moles of CO2? So 1.75 moles CO2 times, all right, I'm getting rid of moles, so they go on the bottom, moles of CO2 I'm going to liters, liters of CO2. 1 mole is equal to 22.4 liters. So this time I'm going to multiply 1.75 times 22.4. That's going to give me 39.2. And I need to check my sig figs. 3, this is a constant, so I can have 3. I'm good. I've got my 3 units, liters, substance, CO2. Okay. All right, so those are all my 1 steps. We're going to look at some 2-step problems now. 2-step problems are just problems that are not in moles or asking for moles. So that's how you can tell you're doing a 2-step problem. Moles aren't mentioned, right? They're like the silent witness. You have to go through moles to get there. So what this tells me is before I convert out to something else, I have to first convert to moles. So wherever you have, take it to moles and then convert to the desired unit. Okay. All right, so we'll diagram some of these out for the first ones. Now, I'm just giving you some examples. I think I'm doing 3 or it might be 4. It's 4. This is not every possible combination you would see, but it's enough for you to kind of like, oh, okay, I see what we're doing here. So pay attention to the process. How many liters are in 5.01 grams? So what you need to think is, okay, I'm in grams. I can't go straight from grams to liters. I don't have an arrow on my highway, but I can go from grams to moles, and from moles, I can go to liters, and that's 2 steps, but I'm only writing 1 equation. I'm going to start with grams. I'm going to convert to moles. I'm going to go to liters. So if I'm in grams, remember that means that I need my molar mass. This case, I need the molar mass of H2. So I have H, I have 2 of them. 1.008 gives me 2.016 grams per mole. So let's set this up. We're going to start with the number given, always the number given in the problem. 5.01 grams H2 times. I've got to get rid of grams, so they're going to go on the bottom. Grams of H2, I've got to go to moles. Moles of H2. 1 mole is equal to 2.016 grams. All right, that's my first thing. Grams cancel. Now I'm in moles. I got to go from moles now to liters. So now I'm getting rid of moles. So the moles have to go on the bottom, H2. And I'm trying to go to liters. Liters go on the top. So now 1 mole is equal to 22.4 liters. Now do you see how my moles also cancel? So what am I left in? I'm left in liters. When I do this in my calculator, I'm going to multiply everything on top and divide by what's on the bottom. So 5.01 times 22.4, enter, divided by, see how it says answer, just plugged in the number I just generated, 2.016. And that gets me 55.6666 repeating for a while. So 55.66667. Okay. Now let's check my sig figs. 3, 4, a constant. So I've got to go 3. So 1, 2, 3. This is going to round over. So my answer is 55.7. Liters are the units that I did not cross out. Liters of H2. Okay. So again, I wanted to go from grams to liters. I couldn't go directly there. I had to go from grams to moles and moles to liters. All right, so let's do another example of a 2-step problem. How many grams of HNO3 are in 4.73 times 10 to the 23rd formula units? So this time I'm in particles and I want to go to grams, but I can't go straight there. I've got to go particles to moles to grams. Okay. And I know because I'm asking for grams, I'm going to end up needing the molar mass for HNO3. So I'm going to just go ahead and get that right now in the margin over here. HNO. one H, one N, three O's, 1.008, 14.01, 16.00. I'm going to add all those up. I'm going to try to save a little space here. 63.018. If you need to see that done out longhand, go back and watch the molar mass video. All right, so what am I starting with? I'm starting with my formula units. So let's start there. 4.73 times 10 to the 23rd formula units, HNO3 times. I need to get rid of my formula units, my particles, and go to moles. So moles of HNO3 goes on top, formula units, HNO3 goes on the bottom. 1 mole is equal to 6.02 times 10 to the 23rd formula units. Formula units cancel. Now I'm in moles. Now I can go from moles to grams. Times, getting rid of moles. Moles on the bottom, moles of HNO3. I'm going to grams on the top, HNO3. 1 mole is equal to 63.018 grams. All right, so now let's type that in. Multiply the top, divide by the bottom. 4.73 times 10 to the 23rd times 63.018, enter, divided by parentheses 6.02 times 10 to the 23rd, close parentheses. And what do I get? 49.514. So I'm going to write that over here. 49.514. Check my sig figs. 3, a constant, and 5. So I'm going 3. 1, 2, 3. The 1 doesn't round, so 49.5 grams HNO3. See why it's important to box off your answers? Because that was messy. But you can definitely tell where my answer is because it's in the box. All right, so we got 2 more of these, and then I'm cutting you loose. Number 3, how many molecules are in 500 liters of HE? So I'm in liters, I'm being asked for molecules. So let's map this out. So this is volume to moles to molecules, so particles. All right, none of this says grams, so I don't have to calculate anything ahead of time. These are nice problems. I just plug in some constants. So 500, don't forget the decimal. Remember, it has sig fig implications. Liters of HE times. Got to get out of volume into moles. So moles of HE on top, liters HE on the bottom. 1 mole is equal to 22.4 liters. Liters cancel, I'm in moles. Then I need to get rid of moles, and I'm going to what? I'm going to molecules. So molecules, remember there's no abbreviation, you got to write it out. Molecules over moles. 1 mole is equal to 6.02 times 10 to the 23rd molecules. 500 times, parentheses, 6.02 times 10 to the 23rd, close parentheses, divided by 22.4. 1.34375 times 10 to the 25th. All right, let's look at our sig figs. 500 with a decimal has how many? 3, right? 500 without a decimal would be 1. With a decimal is 3. 1, 2, 3. The 3 doesn't round. So 1.34 times 10 to the 25th molecules of HE. Okay. And last one. How many molecules of magnesium phosphate are in 143.2 grams? All right, so I'm in grams, so mass, and I got to go to moles, and then I got to go to molecules, so particles. All right, so I know if I'm in grams, I'm going to need molar mass. What do I need molar mass of? I don't see a formula. But what do I see? I have a name. I can make a formula. This is a skill we have. So magnesium is +2, phosphate, PO4, -3 on my drop and swap, Mg3, PO4 in parentheses 2. That's what I've got to get a formula for, or a molar mass for, rather. So Mg, P and O, 3 Mgs, 2 Ps, 8 Os. Periodic table says magnesium is 24.31, phosphorus is 30.97, and oxygen is 16.00. So 3 times 24.31, 72.93. 2 times 30.97, 61.94, and 16.00 times 8, 128.00. And we're going to add all those up. 262.87 grams per mole. All right, now we're ready to go. Got all my parts. How many molecules are in 143.2 grams Mg3PO42 times? Got to get out of grams, go to moles. So moles on the top, moles of Mg3PO42 over grams of Mg3PO42. 1 mole is equal to 262.87 grams times, let's see, my grams went away, now I'm in moles. Go into molecules, so molecules of Mg3PO42 on the top over moles Mg3PO42. 1 mole is equal to 6.02 times 10 to the 23rd molecules. All right, so let's do our math. 143.2 times, parentheses, 6.02 times 10 to the 23rd, close parentheses, enter, divided by 262.87. 3.2794 times 10 to the 23rd. All right, let's check our units, or our sig figs rather. 1, 2, 3, 4, 5, constant, going 4, 1, 2, 3, 4, and that 4 is knocking around. So 3.279 times 10 to the 23rd molecules Mg3PO42. Okay, so before we wrap this up, let's talk expectations. If you're one of my students, what do I expect you to have? I expect you to have your work labeled just like my work has been in every single one of these examples. Number, unit, substance, number, unit, substance, number, unit, substance, number, unit, substance. It's kind of obnoxious. I 100% understand that. But in the next section of stoichiometry, we're going to start switching from substance A to substance B, and it will get real confusing if it's not labeled. So you need to get in the habit of labeling everything like this is right now. Also, you should show me in your answer number, unit, substance, and nicely boxed off, right? This is messy. There's a lot going on here, but there's no doubt what my answer is and where my answer is. If you are one of my students, you will show all work for all problems. No work, no credit. Okay? So these are the steps to do your simple unit conversion compound stoichiometry. Go forth, be awesome.